Hello everyone, Mr. Fawcett here, and today we are going to talk about a concept called the squeeze theorem. Now, this isn't something that you're going to use on a regular basis in an AP Calculus class. It's also not going to pop up in multiple places on the AP exam, or at least I haven't seen it pop up in multiple places. I did see one question that dealt with it on last year's exam, but regardless of how often it's used, it is an interesting theorem and it's part of the course, so we are going to explore it. This video is going to be two parts. The first part is going to be a little exploratory activity leading into the theorem, and then video 2 will be some practice problems on how to use the theorem or to see it in action. So let's look at number 1. It says, let f of x and g of x be defined for all real numbers and be continuous. And we're also told that f of x is greater than g of x for all values of their domain. So what you need to do is pause the video and sketch two functions, f of x and g of x, make sure you label them, where these conditions hold true. And then you're also going to do the same thing for number 2. So number 2, same thing, it says f of x and g of x are defined for all real numbers and they're continuous. And f of x is greater than g of x for all values of their domains except for x equals 1, in which f of x is equal to g of x. So just take a couple minutes, draw out some functions that fit these conditions, and then we'll see if you have the correct pieces that are required. Okay, so hopefully you've had a chance to draw some functions. It says for number 1 that f of x is greater than g of x. So literally all you have to do is draw a function f of x that's continuous and make sure that it is always greater than g of x. And again, the shape of your functions is not important as long as f of x is greater than g of x and they are continuous for all the real numbers. Okay, number 2, same conditions, except when x is equal to 1, the functions are equal to each other. So let's have them both be equal to y equals 2 at x equals 1. But otherwise, the same conditions hold. Okay, so again, your pictures may not look exactly the same as mine, but they should fulfill the initial conditions. All right, we have 2 more problems below before we jump into the actual theorem. So number 3 says, now we have 3 functions. So we have f of x, g of x, and h of x. Again, they're all defined for all the real numbers, and they are continuous. And f of x is greater than h of x, which is greater than g of x for all values of their domains. So same idea as number 1, except we have 3 functions now. So I'm going to draw f of x again up here. Let's put, we'll just make h of x a constant function. How about that? Oops, h of x, not f of x. Okay, it's not g of x either. It is h of x. While g of x will be our bottom function. Okay, so again, the shape of the functions is not important as long as you can tell that the function f of x is always greater than h of x, which is always greater than g of x. Number 4, same conditions, except now we have greater than or equal to. So f of x is greater than or equal to h of x, which is greater than or equal to g of x, except at x equals 1, where we know that f of x is equal to g of x. So it doesn't say anything about what h of x is doing at x equals 1. We just know that f of x is equal to g of x. So let's draw some functions in here that work. Again, I'll use 2 as my, actually I'll just make a parabola for f of x this time. I'm going to draw g of x next. I'm going to draw g of x as another parabola, or something that sort of like a parabola. And now to find h of x, I know h of x has to be between f of x and g of x, at least for every point except for x equals 1. So before I draw h of x, or you've probably already drawn it, but think about what should happen at x equals 1. Where am I going to have to place h of x? Is there a place for me to place h of x based on the initial conditions? Is it possible for me to have h of x be continuous even at x equals 1? And turns out it is. Okay, I can even just keep it as a constant function again. It doesn't have to be constant, but just easier for this example. And because the condition says that h of x can be less than or equal to, it's okay that h of x also equals 2 when x is equal to 1. Okay, so instead of me scrolling down and us losing the graph that we just wrote for number 4, I'm going to erase what we have over here for number 3. And I'm going to just write down the answers for number 5 as we go through them up here instead. So this will no longer be for number 3. Instead, we have number 5. And the first question was, what's the limit as x approaches 1 for f of x? And again, we're looking at a graph for number 4. So we can see, again, we're looking at the pink function. As x approaches 1, it's approaching 2 from both sides, right? And you can trace that. It's approaching the same value. So that limit is equal to 2. Now they ask us for the limit as x approaches 1 for g of x, which is our blue function. And we come over to the graph, and we don't have to trace it, but we could. We can see that g of x is also approaching 2 when x is equal to, or as x approaches 1, g of x is approaching 2. Then the final part, they're asking us, so how could we figure out the limit as x approaches 1 for h of x? And we could look at the graph, but do we have to look at the graph to know what this limit is? Or based on the conditions, could we figure it out? So again, and we'll talk a little bit more about this. This is leading us into the squeeze theorem. But if we know that h of x has to be between f of x and g of x, and we know that f of x and g of x approach the same value at a certain x value, well, there's no other place for h of x to go than squeeze right in between them, right? There's no other place for h to go than squeeze right in between our top and our bottom function. So this limit also has to be equal to 2. And this phenomena is called the squeeze theorem. It also is known as the sandwich theorem. So go ahead and try to explain in your own words. I know we've just talked it through, but explain down below. There's some lines for you to write out your thoughts about why h of x has to equal -2. And your explanation shouldn't just be, well, I look at the graph of h of x that I put on the paper and the limit is clearly 2. No, try to use the fact that we have an f of x function on top and a g of x function on the bottom to try to explain why that middle function limit has to be equal to 2. Then we will move on and give a formal definition of the squeeze theorem. All right, so the squeeze theorem. Given f of x is less than or equal to h of x, which is less than or equal to g of x, around the point x equals a, if the limit as x approaches a of f of x is equal to L, and the limit as x approaches a of g of x is equal to L, so again, in this scenario, Actually, in this scenario, f of x is our bottom function because h of x is greater than f of x, and g of x is our top function because h of x is less than g of x always, or equal to. So if we know that the top and the bottom function's limit are the same, so in this case they're both equal to L, then the middle's function's limit is also going to be equal to L. And you don't actually have to know what the middle function is, or you don't actually have to be able to prove what the limit is of the middle function algebraically, right? It may be one of those tough ones that we're just unable to manipulate. But if we can set up a scenario like this, if we can find a function where if we can find a function that's always greater than the middle function and a function that's always less than the middle function, and then have them both approach the same number at a certain x value, well, then we know that middle function has to approach the same number for that certain x value because it has to be squeezed in between them, right? That's why it's called the squeeze theorem. When we come back for part 2, we are going to put this theorem into action and use it to solve or think about several different problems. Until then, this is Mr. Fawcett. As always, enjoy the rest of your day.